Okay, in this question here, we have a block on a spring and it is given a compression. So it is moved from its equilibrium point by a distance x naught, and then when it is let go, it is given a initial velocity v naught. And we are asked to calculate the maximum speed and the maximum stretch. So we're going to use conservation of energy to calculate this. So total E beforehand is going to be equal to the kinetic energy initial, so the initial push that it's given when it decompresses, plus the elastic potential energy initial, and that will then convert to a maximum kinetic energy. So if we give these the proper expressions, so a half mv initial squared plus a half k x naught squared, because x naught is its initial compression. That's going to be equal to then a half mv max squared. And therefore Vmax, if we isolate Vmax, it's going to be equal to the square root of mv naught squared plus k x naught squared divided by m, which we can then say is the square root of v naught squared. Oh, let's neaten that up slightly. V naught squared plus k x naught squared over m, because, well, first thing we can do is obviously cancel all the halves. Then the m of the mv naught squared will cancel with the m on the bottom. However, kx naught squared will still be affected by the m on the bottom there, so you have kx naught squared over m, leaving you with this final expression here for v naught max. Then what about the total stretch? Well, again, we can say total E is equal to kinetic energy initial plus elastic potential energy initial, and that's going to be equal to then the maximum elastic potential energy. Same idea, we substitute in our expressions here, so half mv naught squared plus a half k x naught squared is equal to a half k x max squared. And once again, we can cancel the halves out, isolate x max, so x max is then going to be equal to the square root of mv naught squared over k plus x naught squared. Okay, so it follows a very similar process to this and leaves us with a final expression as indicated here.